In the last module, we introduced three important theorems. We didn't prove any of those, namely the elementary renewal theorem, then Blackwell's theorem, and key renewal theorem. It's a key renewal theorem, which is of course equivalent to Blackwell's theorem, is going to be the key to many of the applications of renewal theory. So we are going to proceed gradually towards that. As a first step towards that, we discuss and describe what is meant by alternating renewal processes. So essentially, within a renewal, cycle of a renewal process, every cycle of a renewal process, and a cycle means the time between successive arrivals, that would be called a renewal cycle. Within each renewal cycle, there would be one part of time which would be on, the other part of time would be off, and then we prove as a quick application of key renewal theorem some results on limiting probability of the system being on at time t, limiting probability of system being off at time t, etc., etc. Now, as an application of that, first application of that, it turns out that in many models can be actually modeled by an alternating renewal process by defining your on and off periods appropriately depending on what is the quantity of interest to you, as we'll see gradually. So as a first application, what we did is, for any general renewal process, we defined what is known as the residual life and the age at time t, and then we found the limiting distributions of residual life and age at time t, but we also examined the limiting distribution of the length of the renewal cycle at time t. That is, that particular renewal cycle that falls at time t, we looked at the limiting distribution of that as well. So here we are going to start looking at applications of renewal process. We already have stated some major theorems and then proved a simple lemma on the distribution of SNT. All of that would be now put to use in these various applications of different kind, which are all very important applications. So first we define the notion of what is called an alternating renewal process. So imagine that you have a system which can be in two states, call them on or off. As you will see later, in various contexts, the interpretation of what is on and what is off would be left to us. Okay, so for the time being, it's just nomenclature. A system can be in two states, on or off. It starts in on state, remains on for a time z1, then goes off, remains off for time y1. It becomes on again, remain on for time z2, then goes off for time y2, and so on. Okay, so this cycle of on followed by off, then on followed by off for random times, this cycle continues. And this whole thing would be called a cycle. So the random vectors Zn comma Yn, that is the pairs Z1 Y1, Z2 Y2, Z3 YT, these pairs are assumed to be IID, which of course would imply in particular that the Y's are IID and the Z's are IID. However, important to note here at this point of time itself that we are not assuming that Z1 and Y1 are independent or Z2 and Y2 are independent. There may be dependence between Zn and Yn, and in many applications there would be. So what it means is that each time the system goes on, it starts afresh. So no carrying over of any previous information. However, when it goes off, the off period is allowed to depend on the previous on period. So let Zn's have distribution H, the successive on periods in a cycle. Yn's have distribution, common distribution G, so successive off periods, and Zn plus Yn, that is the total length of a cycle, an on-off cycle. Suppose that has distribution F. And denote Pt to be the probability that the system is on at time t. Question that we would ask is, what is Pt for large T? In reality, we would be interested in what is the limiting value of Pt. Does it exist? If so, what is it? And here is the theorem. If f is non-lattice with a finite mean, then limit t going to infinity of pt is e of z divided by ez plus ey, where of course we use z for the generic name for the zn sequence and y as a generic name for the y sequence. Now, there is a basic fact from probability which will be used for this proof, and this basic fact is that we have already used a special form of this for non-negative integer valued random variables, but in general for a non-negative random variable, not necessarily integer valued, even continuous it could be, here's an alternative formula for expected value of x, which is, you look at the tail probability, probability x greater than t for all t from 0 to infinity, integrate this with respect to dt, then that also gives you the expected value of x. I mean, it doesn't matter whether x has finite expectation or not. In case x doesn't have finite expectation, this integral would be infinite. Okay. So here's a proof of the theorem. What theorem? Namely, limit t going to infinity pt is expectation of z divided by expectation of z plus expectation of y. Say that a renewal takes place every time the system goes on. So that means here the time between successive renewals is the length of one full on-off cycle. The interarrival times are successive on-off cycles, as I said. That is therefore IID with common distribution f. And note then that the mean interarrival time is mu sub f, which is expectation of z plus expectation of y. By conditioning on SNT, we get pt, that is the probability on at time t, would be probability that it's on at time t given SNT equal to 0 multiplied by the probability SNT equal to 0 plus, remember SNT equal to 0 has a probability, and for open 0 to t we have quote unquote density of or distribution of SNT df SNT s. So the second part term represents the part where SNT is some positive s. So conditioned on SNT being some positive s, probability that it's on at time t, of course that has to be integrated with respect to the df SNT s. Now the first term is immediate. Probability that it's on at time t given SNT equal to 0 is the same thing as probability that z1 is greater than t given z1 plus y1 is greater than t, and that of course is just the ratio h bar t divided by f bar t. Now for the other part, for 0 less than s less than t, the probability that it's on at time t given SNT equal to s is of course by definition probability that z is greater than t minus s given that z plus y is greater than t minus s, and then of course again is h bar of t minus s by f bar of t minus s. Using the lemma now, we would have, because we know the distribution of, so here we have found conditional probabilities of on at time t given SNT. Now we are supposed to integrate this with respect to the distribution of SNT, which was given by that simple lemma. So using that lemma we get this probability of on at time t, which is pt, is given by h bar t plus integral 0 to t h bar t minus s dms. Now notice that h bar, which is the tail distribution or survival function of a distribution, it has to be non-negative and non-decreasing, and secondly integral of h bar t dt, which is the integral of the survival function, integral of the tail probability, and that gives the expectation of the on time z. So as already noted, or note that h bar t, which is a survival function, has to go to 0 as t goes to infinity. So therefore if we take the limit of pt as t goes to infinity, the first term h bar t goes to 0, so we'll be left with what is the limit as t goes to infinity of 0 to t h bar t minus s dms. Now that is where the key renewal theorem comes in, and you can easily verify that it gives the desired result, namely limit of 0 to t integral 0 to t h bar t minus s dms turns out to be Ez by Ez plus y. Now this is because if you go back to the elementary renewal theorem, what it says is that, saw it last time, so you can the key renewal theorem and get that this turns out, the limit turns out to be exactly this. Now on the other hand, if you had considered, instead of pt, you had considered qt, that the system is off at time t, then again you can go to the same mechanism and you will obtain the limit of that is ey over ez plus ey. Okay. So this is some elementary result about alternative renewal process. Now we can apply that for many other situations as follows. So we'll see some applications. So the issue is that many systems which are otherwise different systems can actually be modeled by an alternative renewal process, and results obtained by using the result that we have just proved for alternative renewal processes. So first let's start with a very, very interesting problem application do with residual life and age processes. So suppose NT is a renewal process with inter-arrival distribution f, and assume that f is non-lattice. Define yt to be s of nt plus 1 minus t. It can be thought of as residual or excess life at time t, and at is t minus snt, that is the age at time t. So you can think of it that way. So let's say that you have a certain machine which needs to be renewed every time it breaks down, and the duration of a machine running before breaking down for successive machines can be thought of as IID random variable, IID non-negative random variables, and a renewal takes place when a machine breaks down and replaced by a new machine. So if you think of it this way, then at time t, if you look at the system at time t, you do not know how many renewals have taken place. All you know that the last renewal had taken place at time nt, and the next renewal is going to take place at time snt plus 1. So therefore yt represents residual or excess life at time t. So how much longer is the running machine, the machine that is running now, how much more life it has at time t. Whereas t minus snt tells you for how long the machine running at time t has been running. So yt is called the residual life and at is called the age at time t. So want to find the limiting distribution of both yt and at. So want the probability that yt less than or s as t goes to infinity, and probability that limit of probability at less than or s for every x positive. So here's a picture which explains at time t. Look at this picture. The total length of the total interval between snt to snt plus 1 is xnt plus 1, and the part between snt and t is that length is at, and the length between snt plus 1 and t is that length is yt. So at represents the age of the machine running at t, because the machine was installed at time snt, so it has been running for a period of at, and the life that is left of this machine is given by yt. Okay. For finding the limit as t goes to infinity of p of at less than or s, let's say, fix any x positive. I'm going to convert this into an alternative renewal process. Declare each renewal interval with the process to consist of an on-off cycle first. Second, within each renewal interval, declare the system as on during the first x time period and off for the remaining time period. So for example, if renewal interval itself is less than x, then the system, during each interval, the system is on for the entire period and off for 0 period. Now, system is on at time t means that at is less than or equal to x. So convince yourself of that. By the way we have defined it, the on and off simply means that the event at less than or equal to s is exactly saying that the system is on at time t, because the first x unit of time in any renewal interval, the system would be declared as on. So age is less than or equal to x at time t means at time t the system is on. Okay, denoting x to represent a typical renewal interval, the on time during a renewal interval is distributed as minimum of x, capital X and little x. So by the result on alternative renewal processes, we quickly obtained probability that at less than or equal to s, limit of that, is the same as limit of the probability that the system is on at time t, limit as t goes to infinity. And by what we have proved, the expected value of the on time, which is expectation of z has distribution minimum of capital X and x is the total duration of the renewal. So that expectation of minimum x and x divided by expectation of the total renewal cycle, which of course is nothing but x, and that turns out to be precisely this. You can verify that. So you have x in the denominator, ex in the denominator, that gives you 1 over mu, and one can verify that expected value of minimum x and x, you write it in terms of integral of the tail probability of minimum of x and x, and you end up getting 0 to x f bar u du. Okay, next is suppose I wanted to find the limit of residual life less than or equal to x, limit of that as t goes to infinity, so that will be the limiting distribution of yt. Now declare the system to be off for the last x time period of a renewal interval and on before that. Then the system is off at time t is same thing as saying yt is less than or equal to s. So again, off time is in a renewal cycle of length x is minimum of x and capital X and x, and therefore we get again very similar result. Now you see what it is saying is, it's very interesting. In the limit, residual life and age have the same distribution in the limit. Now does it contradict intuition? Well, after a long time has passed, the process looks the same in backward direction of time. So that's basically the intuition. So the process in the forward direction and backward direction looks the same after a long time has passed. Okay, next I want to look at the renewal interval containing t. So this is another variable of interest, x n t plus 1, which is at plus yt, length of the renewal interval containing t. Here is a exercise which is interesting. Show that for every t, probability that x n t plus 1 is greater than x is larger than or equal to probability that a typical renewal interval x is greater than x. So what it says is, often known as inspection paradox, renewal interval containing time t is always stochastically larger than a typical renewal interval. So imagine a system in which renewals take place at successive points of time. So each renewal interval has a common distribution, but fix a time t, and if you enter the system at time t, then that renewal interval is a random renewal interval of the many renewal interval, which renewal interval contains that time point t that you have fixed. It so happens that that renewal interval is stochastically always larger than a typical renewal interval. Well, try to intuitively see why that is not so unnatural. Anyway, want to find the limit as t goes to infinity of probability that x n t plus 1 is greater than s. So again we'll use alternating renewal process. Each renewal interval is an on-off cycle. Declare the system to be on during the entire renewal interval if the renewal interval is longer than x, otherwise system is off during the entire renewal interval. So here either the system is on for the entire renewal interval and off for a 0 period, or the system is on for a 0 period and off during the entire renewal interval. Now system is on at time t is same as saying that the renewal interval is of length greater than x. That's by definition of on. Therefore, you can easily verify that expected value of on time in a cycle would be integral x to infinity y dfy. So I have to simply see that if you define this random variable, new random variable, let's say x tilde, which is x tilde if x is greater than x, little x, and 0 if x is less than or equal to x, what is the expected value of x tilde in terms of its Yale probabilities, and that's how we get this. So from that, you can easily use alternating renewal process result to conclude that limit as t goes to infinity of probability that x nt plus 1 is greater than x turns out to be exactly 1 over mu times the integral x to infinity y dphi, which says that by going to 1 minus this probability, if you look at the cumulative distribution function of x nt plus 1, then that cumulative distribution function f sub x nt plus 1 at x, limit of that as t goes to infinity, is given by the integral 0 to x y dfy divided by u. So as we said in the beginning itself, that in this module, first thing that we did was introduced alternating renewal processes, where essentially what happens is that within a renewal cycle of the renewal process, there is an off period, there is an on period, there is an off period. The pair of on and off periods over successive cycles are assumed to be IID, although dependence is allowed between an on and an off period within a cycle. Okay. So under these assumptions, using key renewal theorem, we were able to find limiting distributions of the system being on at time t, the system being off at time t, the limiting probabilities of these events. And then we were also looked at the special thing called the renewal cycle at time t. So this means that there are successive renewal cycles, but if you fix a time t, depending on the different random lengths of the different successive renewal cycles, a particular renewal cycle would cover the point t, and it's not fixed, it's not deterministic. So we ask question about what is the length of that renewal cycle which takes the point t. What happens to be the limiting distribution of that? So we first of all made this statement that, which was left as exercise, that this is stochastically larger than a typical renewal cycle. You should be able to understand it intuitively, but then we actually obtained a result on the limiting distribution of that length of the renewal cycle.